Okay, so it seems like no one is joining this meeting. So I'll start talking to myself then. So I'm Aditya Vikram Singh. I'll be one of the TAs for this NPTEL course on concentration inequalities. I'm a student, PhD student at the Indian Institute of Science, and I'll be conducting these live sessions every Saturday from 3 p.m. to 4 p.m., where the goal is to take questions from you about the video lectures or any doubts that you might have. Discuss a few problems from the assignments after the deadline is over, or if you need some clarification about a problem before the deadline, like now, you can ask that as well. And if time permits, and if there is an interest from this huge audience, we'll also take some discuss some general tools and techniques from that week's lectures. Okay, so this is week one. So there hasn't been any submission deadline yet. So I'll just discuss some questions from week zero assignment. Okay, and you can ask questions in between if you want. You can just unmute yourself. Okay, and just ask me questions. Okay. All right. So the first question here is, so the week zero question is basically a sanity check. It's just a basic probability questions just to get you warmed up. And this is the bare minimum that you must know before attending this course. But even if you don't know, even if you don't know these, you can't solve these questions. It's okay. I mean, so the course will be of a character building nature. Okay. So okay. So the first question is, let me just yeah get my pen. Okay, so the first question is that there is a coin with probability of head 0.2, which is tossed repeatedly until the first head appears. What is the expected number of tosses until the first head appears? Okay, um, so you might know that this is the geometric distribution, right? So if we take n to be the first time heads h appears, okay, then we know that n is geometrically distributed. So what is the probability that n equals 1? It's just 0.2, right? You toss a coin, what is the probability of heads? What is the probability that n equals 2? It's that a tails appears on the first toss, so that happens with probability 0.8, and then a heads appears in the second toss, so it's 0.2, right? And so on. So in general, the probability that this random variable n takes value k is that for the first k minus 1 times you have tails, right, which happens with probability 0.8, and on the kth step you have heads, okay, which is 0.2, the probability of heads. Okay, so now you can just compute this. So this is a geometric distribution with parameter 0.2, and you can just compute its expectation. So the expectation of n, right? So this would be 0.2. So 1 into 0.2 plus 2 into 0.8, 0.2 plus, so 3. So what is the probability that n equals 3? 0.8 square to 0.2 and so on, right? And if you just do to compute this will turn out to be 1 by 0.2, which is 5. Okay, so C is the right answer here. And it's intuitive, right? So the heads appears with probability 0.2, which is like 1 by 5. So you need, on average, you need 5 tosses to get one head. Okay, so this is pretty intuitive. Okay, so the second question. So the second question is, a coin with probability of heads 0.9 is tossed 100 times. Okay, so this will generate a sequence of heads and tails, right? So one particular sequence might be H, H, T, P, right? T, H, right? So this is a 100 length sequence. Okay, so now the question is, which of the following events has the higher probability of occurring? Option A is a sequence with 90 heads is generated. And option B is a sequence with 100 heads is generated. So which of these events has a a larger probability of happening. So, okay, so what is the probability? So probability that 90 hits. Okay, so how many sequences have 90 heads? So that would be 100 choose 90, right? So you have a 100 length sequence, choose some 90 spots and put H there, right? And on the remaining spots put T. So it's 100 choose 90 sequences, uh, which have 90 heads, and each of these sequences has a probability of occurring. What is it? So it's like 0.9, 90, 0.1, 10, right? Because 10 tails and 90 heads. Okay, and similarly, what is the probability of 100 heads? So it's just 100 choose 100. So there is only one sequence, right? 100 choose 100 is one. So how many ways of choosing 100 objects from 100 objects? So it's one. And then it's like 0.9 to the 100. Okay, and now the question is which one of them is bigger? So okay, so what you can do is just take average. Sorry, the ratio of these two. So it's like 100 C 90, 0.9 to the 90, 0.1 to the 10 by 0.9 to the 100. Okay. And what this is it's 100 choose 90, right? And 1 by 9 to the 10, right? This is what it is. So that I just cancelled this 90 0.9s. So there were only 10 0.9s remaining, and then there's 0.1 above. So, okay, so this is just 1 by 9 to the 10. And so now we want to see if this is more than 1 or if this is less than 1. So okay, so what is this 100 C90? This would be just 100 times 99 up to 91 by 10 into 9 into 1, right? So the total thing would be 100 by 90 into 99 by 81 into 91 by 9, right? So all of them are all of these fractions are more than 1, so the total is more than 1. Okay, so the probability of 90 heads is more. Okay, so this is what we have. Now let's go to the next question, which is related to this. So consider the same setting as in the problem above, where you toss a coin with probability of heads 0.900 times, and let A be a particular sequence with 90 heads and 10 tails. Okay, so there are many sequences with 90 heads and 10 tails. So let A be one particular such sequence, and let B be the sequence with 100 heads. So there is only one sequence with 100 heads, and let denote it by B. And so between A and B, which sequence has the higher probability of occurring? Okay, so the probability of A, okay, A is a particular sequence. With 90 heads. Okay, so it's just 0.9 to the 90 into 0.1 10, right? And probability of B is 0.9 to the 100. This is a sequence with 100 heads. Okay, so which of these is higher? So it's obvious that sequence B has the higher probability, right? This is higher. So now if we just compare it with question number 2, what we have is that probability of a sequence with 90 heads is more, right? But if you choose a particular sequence, the probability of that sequence with 90 heads is less than a probability of sequence with 100. Okay, so what is happening in question number 2 is that even though the probability of all hundreds is more than probability of 90 heads and 10 tails for a given sequence, there are so many sequences with 90 heads and 10 tails that it overwhelms this one sequence with 100 heads. Okay, so this is what happens in question number 2, and that is why you have that the probability of a sequence with 90 heads is more, right? Probability that your output is a sequence with 90 heads, right? In question number 3, you just fixed a sequence A, and with 90 hertz, and you have again sequence B with 100 hertz, and you want to know what is the probability of that particular sequence occurring, right? So in this case, the sequence B would have a higher probability. So let's go to question number 4. Okay, and so question number 4, right? So this kind of argument will be used many times during the lectures. So let X be a real valued random variable. Okay, I might be going too fast, so just stop me if you have any questions. Let X be a real valued random variable, and suppose the probability of X greater than 3 is at most 0.1. Okay, so which of the following are always true? So probability, okay, so we have 3 here, right? The probability of X more than 3, so this region is less than 0.1, right? Okay, so the first option is probability of X greater than 6, so 6 would be here, right? So that would also be less than 0.1, so it's of course true because this is a smaller set, right? Probability X greater than 6 is a smaller set, so then probability of X greater than 3, right? So if probability of X greater than 3 is less than 0.1, probability of X greater than 6 would also be less than 0.1. The second option is probability of X greater than 2 is 0.1, so 2 will be somewhere here, right? So this probability can be very high, this probability can be 1, right? If all so this is like at most 0.1, and suppose like it has like 0.9 here, right, between 2 and 3. So this probability can be very high, so this option is not correct. Probability of X less than 2 is at least 0.9. So okay, so we have probability of X greater than 3 is less than equal to 0.1. So right, so probability of the complement would be X less than equal to 3, that would be greater than 0.9. Okay, so right, so these two statements are equivalent. The probability of X less than equal to 3 is at least 0.9. So probability of X less than 2, would it also be at least 0.9? So again, that might not be the case, right? So we are saying that, so 3, right? This probability is at least 0.9. So if 2 is here, is this probability also at least 0.9, right? That might not be the case because there might be some mass here as well between 2 and 3, right? So this is again not an option. I mean, this is an option, it's not a correct option. So again, so now the final option is probability X less than 4 is at least 0.9. So 4 would be here. So we are saying that probability X less than equal to 3 is at least 0.9. So this is at least 0.9. So of course this thing would be at least 0.9, right? So again, this is the correct answer. Okay, so the final question. Suppose X and Y. So let X, Y be a pair of real valued random variables defined on a common probability space, right? So defined on a common probability space in the sense if the sample space is this, right? So X is a real valued random variable. So okay, and Y is also defined on the same sample space. Okay, these are X and Y are measurable functions on this sample space, omega. So okay, so we have that X comma Y is a pair of real valued random variables defined on a common probability space. Okay, so suppose that probability of X equals 2 is 0.2 and probability of Y equals 2 is 0.2. Which of the following are true? Okay, so these are marginal distributions, right? Probability of X equals 2 is this, probability of Y equals 2 is this, but it doesn't tell us anything about how X and Y interact, right? So this is what this question is meant to test, whether you understand this particular concept of coupling, where you have like a marginal for X, marginal for Y, but what does it tell you about a joint distribution, right? So it may not tell you very much. That is the point. So the option A is probability of X equals to and probability of Y equals to. Sorry, probability of X equals to and Y equals to. Okay, this joint probability, what would it be? So this option claims that it's 0.04, which is like 0.2 into 0.2, right? But this may not be correct, right? This only happens, or this happens if X and Y are independent. right? Otherwise, that doesn't happen. I mean, it may still happen, but you don't know whether this happens or not, right? So if they are not independent, this might not happen. So option A is not correct. So whenever the question asks which of the following is true, you have to answer those options which are always true, no matter what, right? So this may happen or may not happen, option A. So we just cross it. Uh, Option number B is probability of x equals to y. Okay, so okay, let me draw a diagram. So suppose this square is the sample space. Okay, right, and this has like points in it, right? So this is like full of points, and these points have certain weights, certain probabilities, right? Uh, and suppose x equals 2 in this part of the sample space. So x is 2 here, right? And everywhere else x is 0 or anything, right? And suppose okay, so now so it might be the case that y equals 2 is this part of the sample space, right? And y is 0 elsewhere. So you have like y is 0 here, x is 0 here, and like x is 0 here, y is 0 here in the remaining part, right? So and the area of this part is the area of this part, right? This is like 0.2, and again the area of this part is again like 0.2, right? And the remaining is 0.6, right? So you have the probability of x equals 2 is 0.2, probability of y equals 2 is 0.2, but probability of x and y both being 2 at the same time is 0, right? The probability of that happening is 0. So, right, and so that is one possibility. There might be another possibility where x is 2 here, y is 2 here, and everywhere else x is 0 and y is 0, right? So again the probability of and this the area of the shaded region is again 0.2, and this is 0.8. So again the probability that both x and y are 2 is 0.2, right? So it may be so that the probability of x equals to y equals to that that may be 0. It may be it may also be 0.2, right? Like in this case it was 0 in this case, right? And and again you may have situations like you have x equals here and then y is this, right? So x equals 2 in this region, y equals 2 in this region, and there is some intersection here, right? So in that case you will have uh, some probability, right? So again, so this option B is not correct because uh, can be 0.2, right? Right, like here. Probability of x equals 2 and y equals 2 is less than equal to 0.2. So okay, so this is correct. So probability of x equals to itself is 0.2, is less than 0.2, and this is asking for more, that the part of the sample space where both of them are 2. So that will only reduce the probability. So this option is correct. And option D, information given is sufficient to claim anything, right? So this is, yeah, we claimed C. So this option is again wrong. Okay. So yeah, these were the questions from week 0. I hope it's clear to everyone. I mean, these are just, yeah, simple questions just to get you pumped up. Um, right. So everyone is very awfully silent. So I'll just maybe discuss some things from the lectures. So the in this week 1 lectures. So this is like from week 1 lectures. The one of the main inequalities used there was this Markov's inequality, right? So this is a very important inequality because we derived the Chernoff bound, right, using Markov's inequality. So once you know the Markov's inequality, you can also derive Chebyshev's and Chernoff, and write a lot of useful inequalities using Markov's. Okay, so this is an important inequality here. Yeah, I don't know what I wanted to say here. Yeah, so just to give you an intuition of what is Markov's inequality, right? To suppose uh, right, you conduct a survey, right, and the average salary is say 100. Okay, so this is a sample space. These are people, right? Amar, Akbar, Anthony, Parminder, right? Rukhsat. Yeah, right. So these are people here, and you ask a salary of from each of them, and you compute their average, and it turns out to be 100, right? And then, okay, so someone comes to you and claims the following: the average salary is 100, and uh, more than half the people earn at least 500. Okay, and you look at this and it looks reasonable, right? Okay, average salary is 100, more than half of them, earn at least 500. Okay, it's like a piece of news, right? You just read it and move on. But if you just stop to think about it, if if more than half the people earn at least 500, okay, in that case, let's see what happens. So suppose exactly half the people earn exactly 500, right? And suppose other half earns zero, right? So in this case, what would be the then average salary would turn out to be what? It's like half the people earn 500 plus half the people earn zero. So this is like 250, right? And you're is claiming here that more than half the people earn at least 500. So this implies that the average salary is at least 250, right? Whereas what you claim in here in the first line is that average salary is 100, right? So this is a contradiction. I don't know what's the sign for contradiction, but yes, this is a contradiction, right? Both of these statements cannot be true, right? So this is something what this is basically the proof of Markov's inequality, where right. So suppose exactly half the people earn exactly 100, and other half, suppose in the worst case, right, they earn zero. They cannot earn less than zero. So right. So even if they earn zero, the other half, we assume the worst about them. Even then, the average salary will have to be more than 250, right? So this is what Markov's inequality says. Basically, Markov inequality is like probability that x, right? Suppose x is the salary, is less is at so what is the probability that x is at least 500, right? So this will be less than equal to expected value of x by 500, and when expected is the average. So average salary is 100, suppose, right? 500, so 1 by 5. So only a fifth of people can earn more than 500, right? And so this is Markov. This is what Markov's inequality says, right? So this statement here, this, let me have the red mark. Okay. Oh, everything is right. So okay, so this statement, this would be in contradiction to Markov's inequality. And this is kind of intuitive, right? So people earning 5 times the average, they have to be less than 1/5 of the total population. Otherwise, yeah, otherwise average won't match with whatever you have put. So yeah. So this is Markov's inequality, and then this is a very simple inequality. And then using this, you have like the entire concentration inequalities course here. Right? So, okay, so the other main thing which was discussed in this lecture and will be important throughout the course is the notion of convexity. So we know what a convex function is, right? Convex function is any function which looks like this. This is a convex function. So for instance, e to the x, right? This is a convex function. E to the minus x is also a convex function. It looks like this. and then right fx equals say x, a linear function. This is also convex function. Okay, and so basically the definition of convexity is you choose any 2 points in the domain. Okay, so suppose this is a domain, choose any 2 points A and B, right? And then yeah, this line here and connecting FA, this would be like FB, right? This line would float above this function graph. Right, so this is basically the definition of convexity, that f theta A plus 1 minus theta B is less than equal to theta f of A plus 1 minus theta f of B for all theta in 0 to 1. Right, so you have these points A and B. So let me draw y-axis here. Right, this is FA, this is FB, and the theta FA plus 1 minus theta FB would be some point. Right, so so this might be theta A plus 1 minus theta B. Right, and then the line would be here, right? So basically it's just that okay, there is someone joining. Hi Sandeep.
Yeah, hi Aditya.
Yeah, so I think there is no one else here. So
Okay.
yeah, I was just clearing my own doubts then. So
Okay.
yeah, if you have any questions, yeah, you can just ask me.
Sure.
Um,
So, Aditya, when I was looking at the first week of lecture, no,
hmm,
the definition of central limit theorem that was used
hmm.
was very different than what I read it when I studied my first course in probability.
Okay, so let me see. So definition of central limit theorem.
The first example, no, which starts with that 50,000
Yeah,
hits and
yeah,
we
yeah, yeah.
like that 10,000 tosses, so we're expecting 5,000 hits,
Hmm.
and we say we can get it out tighter bound using a central limit theorem.
Yeah.
And that bound just appears, right, saying it's from the central limit theorem.
Oh, yeah, yes. Okay, there's someone else waiting to join. Uh, Hi PMRF support. So
Hello, sir. Is there everything's going fine, sir?
yeah, there is only one person at the moment,
Okay,
and
then
and
they may join.
yeah, yeah. So yeah, and he joined just now. So yeah,
Okay, thanks.
yeah. Uh, so okay, Sunny. So we have these x1, x2, right? These random variables, and so what central limit theorems, and suppose they have like mean mu and variance, say 1, right? So right. So we basically look at this thing, right? We have like xi minus mu, right? And we just say that this distribution, this random variable, call it yn. So this random variable will behave more and more like a normal random variable as n tends to infinity,
Yeah.
right? So right, this is what is central limit. So formally, what it says is that okay, so once you have this y, so okay, so now we have a new sequence of random variables y1, y2, yn, and so on. And what we are saying is that our distribution of yn, it tends to distribution of the normal uh, 0 1 random variable as n tends to infinity. So what this means is that if you want to compute probability that yn belongs to some set A, suppose, that will be approximately equal to the probability that z is in A, where z is the normal 0 1 random variable. So for big N.
So this will not be true for every random variable y1, y2, y3, is it?
Yeah,
It will
it
only
won't
be
be
at
true
y
for
dash.
yeah. So that is what was the motivation of introducing this kind of thing. That this is just an asymptotic result which says that as n gets big, this will be approximately close, right? and this will be exactly same at n equals infinity, which doesn't mean anything. So
Why do we say when n gets big, we are not adding the random variables here, right? They're just like n set of
oh no
x.
no, so so
Same as y
so
as that transformed of x.
so yn is this.
Okay, acha,
So
sure.
in the definition of yn,
This is true only for large values of n.
yeah. So for large values of n, this sum will which yeah. So this distribution of this quantity will
This yn will approach the standard normals. The CDF of yn and CDF of
hmm,
standard normal
will
will
come
approach
closer
the
and closer.
standard normal.
Yeah, yeah. So basically, you can use the formula and everything, which you know for the standard normal for yn as well. But yeah, but for very large.
No, but in the lecture we were using a variable q. I'll just
Oh,
open
right.
it.
So what? Okay. So this was for arbitrary set A. So suppose if I say what is the probability that yn is more than x. Okay. So in this course we are basically interested in these types of. So this is called a tail probability, right? So tail probability is that what is yeah, what is the probability that it takes some extremely large values, right?
Mhm.
Or so yn greater than equal to x. So this would be approximately same as probability that z greater than equal to x, where z is the standard normal random variable.
Mhm.
And so if you just have the standard normal random variable here, and suppose x is here, so it would just be this area, right? This would be probability that z is uh, greater than equal to x.
Yeah.
And so this area is this is just the q function. So q of x is basically integral from x to infinity, and yeah, whatever the 1 by
Q is
root
the
2.
CDF function, is it? Oh no, it's the PDF.
You know, yeah, it's the integral of PDF from x to infinity. So
Okay.
it's like 1 minus CDF. Uh,
Uh-huh.
so
And then
CDF,
divided by half, is it? Like, do we assume both the tails being symmetric?
no, no.
Or
So yeah, it's just one-sided thing. So um, so when we say QX, it's like on just on one side, this tail. What is the thing? Yeah. And so so CDF, suppose we denote it as FZ of x, that would be 1 minus Q of x, right? 1 minus Q of x is this area.
yeah,
Probability that Z is less than x, which is this direction. So
yeah.
yeah, so it's basically the same thing, but yeah.
Yeah. So in the lecture we were saying, the number of hits, the expected value 5,000 plus minus square root of number of trials into Q inverse.
Oh, right, right. So what that was that okay, so that happens when you want a certain probability that, so suppose you want to estimate this probability of,
Acha,
so
once I put the confidence value and I
yeah,
fix
yeah,
the
yeah.
n for that confidence value, then it
Yeah,
works.
you fix the confidence value, and then what is the x for that confidence value, right? So
The n is that? Oh no, the
no, it won't tell you the n. So that is the problem with central limit. It just says that for large n. So during the entire calculation, we are only working with the normal distribution,
hmm
right? And so we only work with the normal distribution and say that for large n, yn would be approximately the same. So yeah, so that was that thing that okay, so you put qx as say delta, the confidence, right? So x
So
would
you're
be what?
saying Q is actually the Gaussian's CCDF.
Yeah, it's called CC complementary CDF because it's 1 minus CDF.
Okay.
Yeah, yeah.
Huh. Sure. So essentially, it is central limit theorem then.
Yeah, yeah. So it's
Yeah.
the same as central limit theorem. It's just once you have confidence, so q of x is delta, so x would be q inverse, right, of delta,
Sure.
right? And that is why that q inverse appeared there. Uh,
Sure.
yeah, but it's yeah, it's just the central limit theorem.
Sure.
So but yes, go ahead.
No, I was just wanted to ask, what's a is there a more benign text to understand constitution inequalities besides the Oxford text, which I find is a little dense.
Yeah, that text is a bit. Actually, that text is the benign text, and that is the text that made this concentration inequality accessible to like engineers and everyone.
Acha.
Otherwise, before that, it was like a pure mathematical thing, and yeah, we had like concentration of measures. There was a book called Concentration of Measures, which was in terms of like measure theory and everything. So this was one of the
Uh-huh.
so okay. So what you will see in this text, and even through this entire course, is that all the steps are elementary, right? So all the steps are just either Cauchy-Schwarz inequality or Jensen's inequality or AMGM inequality, right? That kind of thing, or basic probability. But how you thread together all the steps, there is where the ingenuity lies of this book and of this, yeah, the course as well.
So
So
what is the prior background we need? Like what sub areas of probability you should be good at before you attempt concentration inequalities?
so
What
you
should be
just
clear?
need the
Just
usual.
understanding the theorem and law of large numbers would be good enough, is it?
Yeah. So you just need the basic in whatever the first course in probability is. Uh,
Okay.
yeah, that and you should know some basic inequalities, right?
Uh-huh.
So for instance, so are you aware of these convex functions and everything?
Yeah, I'm aware of what a convex function is.
Yeah, so that's what I was clearing my own doubt. So what here? So what is right? What a convex function is basically a function where the line lies above the function, right?
Yeah.
For any 2 points in the domain like A B, if you join FA to FB, that line will lie above this the graph of the function. So
Yeah.
this is what is convex function, and one of the main inequalities for convex function when it comes to random variables is this Jensen's inequality,
Mm-hmm.
right? And so Jensen's inequality basically says that if you have a random variable x and you are interested in this f of x, okay,
Mm-hmm.
so in this case, what is the relation between f expectation of f of x and f of expected value of x, right? So suppose you have a random variable x and you are interested in this e power x, right? And for some practical application you are interested in e power x, and now you want to find the average of e power x. Okay, so one intuitive thing to do would be, suppose x is the number of times heads appears in 100 tosses. So it would be like, it's, yeah, you might say that it's approximately like e power 50. So number of heads in 100 tosses, right? So what we have done here is we just substituted e power expectation of x, right? Which is, so right, you might have these kinds of things, but how are they exactly related? Like, you wanted to compute expectation of e power x, instead of that you have computed e power expectation of x. So Jensen's inequality just tells you that, yeah, what does it tell you? Yeah, it tells you that expectation of f of x would be more than f of expectation of x.
Mm-hmm.
So right, so this is for convex f. So this is where convexity convex. Okay, so one graphical way to see this would be, suppose, um, yeah, so you have this convex function, and your random variables, suppose it's a discrete random variable, it just takes like x1, x2, or x3, okay, with certain probabilities. So your random variable x is x1 with probability, uh, say p1, right? And x2 with probability, p2, and x3 with probability p3, right? So and you are interested in f of x, where f is this convex function, right? So, oh, what happened? Right, so you're not interested in x, you're interested in f of x. So it will be like f of x1 would be this, f of x2 would be here, right, and so on. So yeah, so the thing is that if you just, mm, yeah, so if you take these f values and just connect them like this, all the line segments are above this function because of convexity, right?
Mm-hmm.
So the entire triangle would be above the function,
Mm-hmm.
right? And now when you compute the average of the function, it would always lie inside this triangle, uh,
Mm-hmm. Yeah.
right? And so because the entire triangle is above, and you're taking like average of these 3 points basically, right?
Uh-huh.
And so the average would be inside the triangle, and the triangle is above this graph of the function, right? So this is what it is basically saying, that f of expectation of x. So f of expectation of x would be the graph of the function f, because there's an f outside. F of expect is
Yeah.
would be less than expectation of fx. So expectation of fx would be here somewhere, right?
Expression of x will be on the line, is it? Or no, it will be inside the triangle.
Yeah, it will be inside a triangle somewhere, and
Okay.
suppose it's here, and the corresponding, yeah. So f of expectation of x would be this, the graphical point, or the point on the graph, and expectation of fx would be this inside the triangle. And so this is basically what Jensen's inequality says, right? So
Uh-huh. Like intuitively, how do you see it would be inside the triangle? Expectation of
yeah,
x.
yeah. So yeah, let me see. I just said this. So let me. Um, okay. So if we, right. So if you have, like, suppose if you just consider like x1 y1. So suppose this is like x1 y1. This is x2 comma y2. This is x3 comma y3, right? And if you take suppose average value of these 3 points, okay,
Mm-hmm.
so it would be, suppose, like p1 times x1 comma y1 plus p2 times uh, x2 comma y2 plus p3 times x3 comma y3. So that would be inside, that average point would be inside this triangle. Uh, so right, because the height has to be the average of these three. So the y coordinate would be the average of these three, and x coordinate would be the average of these three. And so that point would lie completely inside this triangle, right? And so what would be this point? So this point would be, it's like p1 x1 plus p2 x2 plus p3 x3 comma p1 y1 plus p2 y2 plus p3 y3, right? So,
Mm-hmm.
and yeah, so yeah, so that is basically the
It would
explanation.
be the centroid of
Yeah, the
the.
centroid, yeah, exactly, centroid or center of mass. Or yeah, so that, yeah, that is a better way to understand it. So this is what is,
And that will be, of course, more than the function.
yeah, that would be more than the function, right? So
Sure.
yeah, at this point the function value is this, right? And your expected value of f is this, and right. So
Mm-hmm.
so this is this is so this is for discrete random variable. In general, it holds for like any random variables, right? So
Mm-hmm.
if you have 4 points, it would be a rectangle, and or like a normal parallelogram or something. So uh, yeah, and then again from Jensen's, you can get all these AM GM inequality, right? Those are okay, like a plus b by 2 is at
Is
least
then equal to root AB.
root ab, or you can have like a plus b plus c by 3, right? Root ab,
Yeah.
like 1 by 3, and so on, right? So yeah, so even these inequalities, you can just use Jensen's to see why these are true. So if you just take log on both the sides,
Uh-huh.
so it would be like log a plus b plus c. Yeah, I don't know why this is not working properly. Okay, a plus b plus c by 3. Okay, and so this is LHS. The right hand side would be,
1/3 of log A plus log B plus log C.
yeah. So again, you're saying that, right? So if you just take random variables as a, b, c, each happening with probability 1 by 3, 1 by 3, 1 by 3.
Mm-hmm.
So what the left hand side is, log of the expected value, and what the right hand side would be, expected value of log, because it's like 1 by 3 log a plus 1 by 3 log b plus 1 by 3 log c.
Is it expected value of log?
Yeah,
Log of expected value, sorry. Log.
so the left hand side is log of expected value, because a plus b by plus c by 3 is the expected value,
Yeah.
right? And what is the right hand side? It's like 1 by 3 into f of
Okay.
a
Yeah,
plus 1 by
sure.
3 into f of b, right?
Yeah.
So this gives you the AMGM inequality for, right? And then again
Uh,
between, again you have this inequality that a plus b plus c by 3, suppose, uh, is greater than the harmonic mean. Harmonic mean would be 3 by 1 by a plus 1 by b plus 1 by c.
Yeah.
Right. So again you can again see this. Here again a, b, c would be random variables. Sorry, the values which the random variable can take, and here the fx would be 1 by x. So you can just try this. So again, once, so 1 by x is again a convex function, looks like this.
But this used to work only for convex functions, right? Here A, B, and C we're assuming are convex.
No, no, so a, b, c are just particular values.
They're constants, right?
Yeah,
But
the,
wasn't convex inequality true only for convex functions?
so
The
so
Jensen
yeah,
inequality.
yes. So yeah, so it's not like it's not a direct application. So like even here, if you just see AMGM inequality, we had like a plus b plus c by 3 is greater than something. We want to prove this, right?
Mm-hmm.
So now what we did was we defined some random variable x,
Oh,
and
the log of x is a
ye-
concave function or
yeah,
anti-convex
yeah.
function.
So and then we took log of expectation of x
Yeah, yeah.
and expectation log of x. So similarly, again, you define a random variable x here, which will take a with probability 1 by 3, b with probability 1 by 3, and so on, right? And c with probability 1 by 3. So expectation of x would be a plus b plus c by 3,
Yeah.
right? And then f of expectation of x, if you just compute, you'll see that it's the right hand side. And so again, yeah from Jensen's inequality, basically you get that as a result. And similarly, you can show that gm is greater than hm, again using log. So there is some convex function which will give you these inequalities.
Uh-huh.
And then you have something called Holder's inequality and Cauchy-Schwarz inequality. Uh, you have something called Young's inequality. So Young's inequality is like, it's a generalization of AMGM. So AMGM is what? It's like AB is less than equal to A square plus B square by 2.
This is holders.
No, this is usual AMGM, but I'm applying it on A square and B square. So once you take square root, it will just be AB.
Ah, okay. Acha. Yeah.
So this is like AMGM. And what Young's inequality is like AB is less than equal to uh, A power P by P plus B power Q by Q, okay, where P, Q are both greater than equal to 1, and 1 by P plus 1 by Q is 1. Okay, so suppose P and Q both are 2, right?
Yeah. So then
So
you get AMGM.
you get AMGM. But you can also have like P is say P is 3 and Q is 3 by 2, right? Because we want their reciprocals to sum up to 1, right? So this is called Young's inequality. Uh, and
So
then
which example you told? P is 1 by 2 and Q is 2.
no, so P and Q both have to be more than 1.
Okay.
So suppose you took P is like 3.
One has to be 3, other has to be 4. Okay.
No, no, so no, no, yeah, so we want 1 by P and 1 by Q to sum to 1.
Yeah. Okay. Sorry.
So 1 by Q so 1 by P is 1 by 3. So 1 by
So
Q would have to be 2 by 3,
2 by
and
3. So yes, that will be 3 by 2 then.
3 by 2. Yeah. So I mean there has to be some relation between P and Q. It cannot be like arbitrary P and Q. So that relation is
Sure.
captured by 1 by P and 1 by Q.
Where is
And
this coming from, this inequality?
yeah, so again this inequality, you can just take log, okay, on both sides.
Oh, we can show it again using
Yeah, you
Jensen's
can
as well.
use just Jensen's inequality. And the convexity part is coming because again 1 by P and 1 by Q are summing to 1. So we can treat 1 by P and 1 by Q as probabilities, right?
Uh-huh.
So you take your random variable x takes a power P with probability 1 by P, right?
Okay.
And so it's basically because of that. since 1 by p, you can treat 1 by p, 1 by q as probability, then just show this Young's inequality. So yeah, and then using Young's inequality, there is something called Holder's inequality, which is that it's a general, it's like applying Young's. So a and b here were scalars, but if you want to apply to like functions or random variables, so you have like the one norm of xy is less than equal to the pth norm of x and the qth norm of y. Yeah, so I think yeah, this is the Holder's inequality. Again, p and q.
Coming from Young's inequality, is it?
Yeah, so if you see the proof of Holder's inequality, it would just be applying Young's inequality at every point in the sample space and then just taking expectation on both sides. So that would be Holder's inequality. And the special case of Holder inequality is when p equals q equals 2. That would be Cauchy-Schwarz inequality.
Okay.
So right, so you see everything can be derived from Jensen's, right? And Jensen's inequality is just it just follows from convexity. There is, you can see geometrically, right? The entire thing lies above the graph, and so Jensen's provides one unified framework to see all these inequalities, and so these inequalities will be constantly used. And so in this sense, so these are not simple, but these are elementary, right? You can just you can derive them using very elementary steps. You don't need very high-fi mathematics. So that would be the flavor of this entire course, that the way we argued about these inequalities. Now we'll take these inequalities as given, and then we'll argue about probabilities and things like that to derive concentration results, right? So basically, concentration results we usually want. So like if you design an algorithm whose output is random, right? In general, what we say is that sometimes we are just happy to say that okay, the output matches the true value in expectation, right? But
That's weak law of large numbers, no?
no, suppose you so you okay, so you want it, so it's something like no, so uh, suppose you want to find something, some unknown quantity. Okay, suppose you're getting samples from some Gaussian distribution, and you want to estimate the mean of that Gaussian distribution. So one estimator would be just take the average of those samples.
Maximum likelihood estimator, yeah.
Yeah, so that is, yeah. So in general, estimator is just any function on the samples, right? So in general, yeah. So this you can.
One is we can take average.
Yeah, just take average, simple average, and okay. So now what is how is this algorithm which outputs just the average of the sample? So you can say that okay, if you in expected value, that average will match the true value, right? So if you have so suppose you have like x1 plus x2 plus x3 by 3. This so after seeing 3 samples, this is your output, your mu hat, right? And so what is expected value of mu hat? Just take expectation on both sides, and you'll see that it is the expectation of basically x, where x is the original Gaussian random variable. So in expectation, your algorithm is giving the right answer, but then sometimes you may not be happy in just expectation. You may also want to control how much the variance is, right? So and right, so that kind of thing is addressed by concentration inequalities. Concentration inequality says that if you use concentration inequality, you can say that with probability 0.99, the answer I give will fall very close to the expectation, right? And that how close, that would be determined by that Q inverse kind of thing, right? So that is why.
Give a confidence along with the
Yeah. So
estimator I'm giving, I can give confidence along with the estimator.
Yeah, you can give a proper numerical confidence that, and so your output won't be a single number. It would be a range, right? And you'll say that the actual value will be in this range with very high probability, with very high confidence. So that is
why will it be a range?
Because the concentration inequality would be that probability that your output lies in some interval is
Which for an interval it will give me a confidence value.
Yeah. So in general, confidence values are the intervals. Like if you see the surveys in conducted, it's like they say 95% confidence interval, right? That kind of thing. So those are always intervals that, and this is one of the problems with which with the usual machine learning, the naive machine learning algorithms which we have these days. It's like that machine learning algorithm gives just one value, right?
Mm-hmm.
And you don't know, like, okay, this is a value, and if you just change the input a little bit, right? If it's a stop sign and you just put a cellophane paper over the stop sign and then
Mm-hmm.
pass that picture to the neural network, it will give some other value, right?
Mm-hmm.
So that values fluctuate a lot, and there is no guarantee, there is no theory of what that value is giving in general, right? And
Mm-hmm.
so ideally you would want like your machine learning algorithm or any statistical algorithm to give you an interval and say that the original is in this interval with very high probability, right? So
Uh-huh.
this would be a more principled way of doing things.
And
Uh,
that's what Bayesian ML guys would do, is it?
yeah.
They
So
would use.
the Bayesian ML guys, yeah, they put a prior on everything and then say, yeah, but
Yeah.
yeah, that sounds like kind of ad hoc, that they put a prior and then they say, okay, with this probability.
Uh-huh.
But yeah, that is the kind of thing they try to address.
Sure.
And in
But
free,
how the concentration inequality comes up with this confidence bounds? It's using these kind of inequalities.
yeah. So now you'll use, like, for instance, Markov's inequality, and if you just go through the week one lectures, there's something called Chernoff method and things like that.
Yeah.
So
Chernow bound. Yeah.
yeah, Chernoff bound. So those Chernoff bound, they give very strong concentration, in the sense that you can say that, okay, it's
By concentration, we mean the expected value or the average value.
so by concentration you mean that, okay, so suppose you fix a confidence that I want to give an interval uh, with confidence 0 point, which has the true value with probability 0.99, suppose. Okay, so now if you use a concentration inequality, what you'll get is that interval will be small,
Mm-hmm.
right? So if you use some weak inequality like the usual Chebyshev inequality or something, that interval you might give would be a large interval. Okay, because you're not very confident, your analysis is a little weak, right?
Yeah.
So you're not very confident, so you give a large interval, which is okay, right? But ideally you would want like as small an interval as possible, right? When you give,
Mm-hmm.
because ideally you would want to give like a one particular answer, but okay, that is not possible because the output is random and so on. So you want to give as small interval as possible, right?
Mm-hmm.
and
Mm-hmm.
and so concentration inequalities basically allows you to do that. So that is what is meant by concentration, that all the probability mass is concentrating in that very small interval. It's becoming more
Mm-hmm.
peaky and peaky, right? So very thin and very peaky. So all that 0.99 mass is within that small interval. So
Sure.
so that is what the things is used for. So in this course
So
we'll
like
hmm,
once we're going through the course and we are stuck somewhere, right? Is there a forum we can ask questions or how do we go about it
sorry,
besides this weekly meetings?
sorry, your voice was breaking. Could you repeat it?
No, I'm saying, Aditya, say once we are going through the lectures now and we are stuck somewhere, is there a forum or is there a way to ask a question?
Oh yeah. So there is a discussion forum. Uh, on the Swayam portal, I think there is something on the top called Ask a Question, and
Mm-hmm.
so I will be monitoring that discussion forum, and there is another TA for this course who will also be monitoring that discussion forum, and yeah. So either we'll try to address the question there itself, or we have again these weekly sessions where I'll again address those questions if they are not addressed
Uh-huh.
already, right? So
So how difficult is the course, Aditya? Does it require a lot of mathematical maturity to get through?
Uh, yeah, again, so it's like things look dense, right? But if you just go step by step, it's not very difficult, right? So
Mm-hmm.
that is what this course is. It's like all the steps are elementary, but the way they combine, it gives you a very unique, a very like strong result, right? So that is the flavor of this entire course. So again, if you go just step by step, which I mean, you can just yeah, just go through the lectures, and any step you're not comfortable with, just ask in the discussion forum or these weekly sessions. And
Mm-hmm.
yeah, and I think it's good. Even if you just so even if you don't want to do the entire course, if you do the first 2 3 weeks,
Mm-hmm.
that will give you a lot of tools to deal with all those the inequalities in all the modern machine learning and statistical papers, right? So
Okay.
most of the inequalities will be covered in the first few lectures, and then if you want to dig deeper and look at more applications, then yeah, it
Uh-huh.
yeah.
And do you recommend going through the textbook or lectures would be good enough?
Yeah, the lectures would be good enough. So yeah, I haven't gone to the textbook myself.
Okay.
I've just yeah, just the lectures, and if you think some point is not clear, you can just look at the textbook.
Sure. The
But
Oxford one, right?
yeah,
Oxford Press one.
the concentration inequalities by Yeah, the French authors. So yeah, so I don't think you need to go through the textbook.
Sure. And is there the way the question, the asker dot works? It would be like through Google Mails, is it?
Yeah, it would be a Google group. It's a Google group basically. Yeah. And so
Okay.
you post a question, and yeah, it's a public forum, and everyone can see the
Okay.
question. And when I answer, everyone can see the answers. Like,
Sure. So,
yeah,
Aditya, are you in ISC kya? In
yeah,
the
yeah. I'm
Asker or with Himanshu?
yeah, I'm under Himanshu. Yeah,
Okay. You are a PhD student, is it?
yeah, PhD student. So yeah.
Okay.
So yeah, they taught this course during, to me, this was taught during those pandemic days. So again, it was like a virtual
Okay.
classroom. Yeah, the recorded lectures again. So, but
Okay.
but but they used to have this weekly live sessions as well with the students of the course.
Uh-huh.
And so
Mm-hmm.
yeah,
That's a lot
the
more important, no, to keep it human. Otherwise, it's just
yeah,
like
yeah,
Zoom
the
lectures all
NPTEL,
day.
the NPTEL course in general, like if there is no weekly interaction, then it's very boring, right? It's like,
Yeah, yeah. You lose interest, right? You feel lost. Ki,
yeah, you
what
feel
will be the
lost.
case today?
Yeah, you just view at like 1.5x or 2x, right? All the videos, and
Yeah.
depending on your patience, and yeah, it's like horrible.
Mm-hmm.
So yeah, this week,
Uh-huh.
that is why we have this weekly session, just to, right, bring a human element in. Yeah,
Sure.
yeah.
Aditya, whenever I come to the institute, can I come and say hi? I do work closely with Professor Pratosh, same department.
Oh yeah, yeah, sure, no problem. Yeah, we can meet whenever. So
Sure.
yeah, yeah,
Can I
just
get your email or something? How do I reach out to you?
yeah. So my email, I think, okay. So it's like adityabs at gmail. Sorry, at isc.ac.in. So it's Aditya VS. Okay, Vikram Singh. So,
Okay.
so yeah, just drop me an email anytime you're here, and we can. Yeah, no problem.
Sure.
Yeah, yeah,
Sure. So I'll go through the first week of lectures and then probably I'll put it up in the forum and then we'll have this weekly thing, no?
yeah,
Every
yeah. We'll have
Saturday,
this weekly thing, so you can get,
same time
yeah,
Saturdays.
yeah, same time 3 to 4 every Saturday.
Sure.
Yeah,
All right, Aditya, and I'll cover up week one and I'll come
yeah,
back.
yeah, yeah, sure. Okay, yeah, okay.
And this set of problem sets also that we can try.
Yeah, so you have the assignments in the, so for
Okay.
every week there is a weekly assignment.
Okay.
So you can go through the questions. If you have any problem in the problem understanding the question, you can ask them. And once the deadline is over, then I can discuss the solutions as well.
Okay, sure.
So I think it's like every 10 days you have to submit these are multiple choice questions. So
Acha.
10 questions, and yeah, so uh, yeah, so I and one other TA, we had created those questions based on all the lecture material, and
Mm-hmm.
so those questions is basically, if you're planning to take the exam, those questions will prepare you for the exam. And
Okay.
those questions will also help you understand the lecture. So if you can solve those questions, you basically more or less understand the lecture at a decent level.
Uh-huh.
So yeah,
Sure. Aditya, how useful has it been while practically doing ML, using concentration
yeah, yeah. So
inequality? How
so
common is
that's
it?
why I said, like,
Or it's very rare?
yeah. So like Hopkins inequality and Bernstein's inequality, these are some inequalities which are used a lot. So,
Okay.
and these would be covered in like the first 2 3 weeks. Uh,
Okay.
so those will be used a lot. But this course is basically about a technique
Mm-hmm.
that, so for your specialized problem, how do you derive concentration inequalities for that, right?
Mm-hmm.
What quantity should you look to bound when you want to derive a concentration inequality? So
Mm-hmm.
the thing in the course is that there is something called a moment generating function, and if you have a
Mm-hmm.
good bound on the moment generating function, you have good concentration. So
Mm-hmm.
right, so moment generating
We
function
need
is,
we need to know prior, is it? What is the moment generating function? Or it will be taught.
yeah, so it's there. Moment generating function is just expected value of e power lambda x,
Okay.
right? So where lambda is some constant and x is the random variable. So instead of looking at expectation of x, right?
Mm-hmm.
So Markov inequality just looks at expectation of x. Chebyshev
Mm-hmm.
also looks at like variance of x. So basically expectation of x square.
Mm-hmm.
So here in MGF, you look at all the expectations like e power lambda x. If you just
Mm-hmm.
do the power series of e power lambda x, it's like 1 plus lambda expectation of x plus lambda square expectation of x, the whole square, that kind of power series. So
Okay.
so basically MGF covers all the moments basically. And so if MGF
Okay.
exists, it gives a very strong concentration inequality because all the moments exist and they are bounded and so on. So
Okay.
yeah. So, yeah, so there is nothing you need to know a priori about what MGF is. Like all